Welcome to Study Loop.
In problem 11, we will compare two different atoms. First one will be uranium, and the second one will be tin. So what we're asked to do is to calculate the binding energy per nucleon for those two atoms and then compare them, because from the binding energy per nucleon, we will be able to determine which of those atoms is the most stable. But first, let's calculate the binding energy. And to calculate the binding energy, we need to know the mass defect. Mass defect is delta M. And as you could see in the previous video, it's equal to the sum of the constituents minus the mass of all the constituents minus the mass of the atom. So for uranium, this is equal to 92 protons, are actually hydrogens because it includes one electron, plus now we have to calculate the number of neutrons in here, and for this we will simply do 238 minus 92, and that gives us 146. So 146 times the mass of a neutron minus the mass of the whole thing together, which you can find in the table at the end of the manual. And so that is 238.050.784. Oh. Just to be a little more consistent with my notation, I wasn't ready yet to write this. So let's just say the mass of uranium. Good. So I'll say we'll calculate this one on the next tab, and we'll keep rolling with this one, with uranium. So that would be 92 times 1.007825 atomic mass units, which is the mass of a hydrogen atom, plus 146 times the mass of a neutron, 1.008665 atomic mass units. And then this is what I was writing up there, 238.050.784 atomic mass units, which you can find in the table at the end of the manual. Now, this sums up to 1.934206 atomic mass units. Okay, great. So now to calculate the binding energy of this one, we'll do this times c squared. As given by this formula. And remember that UC squared is 931.5 mega electron volts. So that the binding energy for uranium is 1,801.7 mega electron volts. Right, let's move on with tin. We have to do the exact same thing with tin to be able to compare them. So the mass defect, we'll start with 50 times the mass of a hydrogen atom. That accounts for the 50 protons and for the 50 electrons. plus 70, because 120 minus 50 is 70. 70 times the mass of a neutron minus the mass of tin. And so this is equal to 50 times 1.007825 atomic mass units plus 70 times 1.008665 atomic mass units minus 119.902197. And it's very important to keep all the digits they give you here because we're dealing with very, very small numbers. Very high precision for this kind of things. And so that gives me mass defect of 1.095603 atomic mass units. And now to calculate the binding energy for this, well, we just have to do the mass defect times c squared, so 1.095603 U times c squared. And remember that this is 931.5 mega electron volts. So this number times 931.5 mega electron volts gives me a binding energy of 1020.6 mega electron volts. Okay, but we're not quite done because we can't really compare those. Because if we compare those binding energies, uranium will have an unfair advantage because it has a lot more nucleons. And so the more nucleons you have, the more energy you have by default, and that's cheating. So to think of an atom in terms of stability, we really have to think of it as energy per nucleon. How much energy does each nucleon bring to the atom? And so for uranium, the binding energy per nucleon is going to be, well, what we calculated here, 1801.7 mega electron volts, but we have to divide by 238 because that's the number of nucleons there is. So that gives me 7.57 mega electron volts per nucleon. And then for tin, the binding energy per nucleon will be what we calculated here, 1020.6 mega electron volts divided by 120 nucleons, and that gives me 8.5 mega electron volts. You can even add a 0 here for extra precision. Okay, so there we go. We found our binding energies per nucleons for both the atoms that we were asked to do. Now, which one of those is more stable? Well, it will be the one with the biggest energy per nucleon. So the more energy per nucleon you have, the more energy it would take to break the atom. And so uranium has a lower binding energy, so it's easier to take the atom, to take the protons and neutrons out of the uranium than it is to do with tin. So most stable is tin.